Okay, so it looks pretty much like it does. I was going to say it looks pretty much like it does in the drawing, but maybe it doesn't. Anyone? Oh, there's a picture of the latest one on this handout, or reprint. There are 3 different pieces of stuff.
What are you doing?
So part of the of what you have in the drawing, this one, pretty much describes what's on this plate right here. And the film goes into this the inside drum. And there's one part that you don't see here, and that is, well, you don't see it at all, is the rotating prism, which connects to the rotating drum way of this connection here. So you line things up, and now when that starts to turn, the mirror starts to turn. I think I can take this apart. I think I can, but I won't. I guess the drawing also shows that this is a through the lens system. And as you'll see, there is a mirror and a ground glass, so you can look at the image, and there's the lens. The ground glass would be in here, and you look at it through this. And the way that you look through the lens is you insert a mirror. That's this. When you do that, there the mirror is in. That means it's behind the lens, sending light up to the ground glass. If you don't take that out of the light path, you don't make any kind of a picture. You got to remember to do this. I didn't do that with at least one of the runs last week, and so if there's nothing on that film, the reason is I forgot that I was looking through the mirror, or through the ground glass, which called for the mirror to be down. And the shutter that I was referring to that limits exposure time to 1 revolution of the drum is right here, right behind the image. We're not going to need that. That is what's called, in the high-speed term, is called a capping shutter. It essentially makes the camera dependent on synchronization. But we're not going to depend on that. We're going to turn the light on and turn it off in less time than it takes the drum to go around once. So we don't need any kind of extra shutter. That means it'll be always alert. And the 2 light paths that are mentioned in the drawing, okay, one of them is here, and the other one is there. Okay, they're 45 degrees apart along the periphery of this drum. And the camera is a daylight load camera, if you're lucky. That means that you could take it out in the field and then load it with photosensitive material. You do it by preloading the film on one of these cassettes. When you could buy them, they were $500 a piece. I was looking for a piece of film. So, you know, you might have a dozen of these, or somebody might. And you get yourself the length of film that you need. And the film goes into these cassettes. There's a a device inside. They're essentially rubber fingers that catch onto the film. Insert it to begin with, beyond those rubber fingers, and then when you turn clockwise, they take it up and they pull it into the cassette until it's all inside. At this point, the cassette can be closed and it becomes light tight. So maybe because these are not perfect, and sometimes they make mistakes, that's why the government got rid of this camera. But whatever, we're going to deal with it as is. And I can't believe it. Okay. Normally it's not so easy. So I'll show you in a second how the camera's loaded, but before that, there's a tachometer here. This essentially is a tachometer, but it reads out in pictures per second. And that's easy to do. You say, well, however long it takes it to turn once, times what? Times 224 for the reciprocal of that gives you the RPM, or times 60, whatever. So all you need to do is provide voltage to the motor. And if you're lucky, and particularly if the power supply is plugged in, the run starts to turn. And already it's running at about 3,000 pictures a second. I don't like something. Oh, now it's okay. It fixed itself. So you just increase the voltage, RPM goes up. The camera's running right now at 15,000 pictures a second. So the camera used to have a brake on it, to flick that on and magnetically it would slow the drum down. That doesn't work anymore. So we just got to wait for this to slow down. The government would say, well, we don't want this. I'm saying, I don't care. These are so unique in the history of high-speed photography. It merits just knowing something about them. Now you can't do that if it's loaded. So anyway, these again, they're an engineering marvel. Somebody who had a lot of time on their hand figured out how to make an interlock system that would not let you make a mistake, at least not as far as attempting to put the film in. So it has a number of settings on it. One of them says, open the cassette. Well, once you do that, this is ready to go in there. So it turns out that as long as when you put this on, it has a number of notches and pins. If you align those properly, in that case you can put the cassette on and you can get it to the point where you can open the cassette, because eventually you want to get the film out of there. So you rotate on the inside drum and the cassette is now open. But the film is away from the drum. You couldn't load it this way if it were touching. But this interlock here allows you to rotate the drum and bring the film so that it's not touching the drum. And behind the film there are some rollers that are hopefully, pushing the film against the drum. Yeah, they more or less work. And at that point, this thing is ready to be loaded, and there are arrows on it that says, rotate this way to load. Dummy. Okay, so you rotate that way, and eventually the film comes off the drum, off the inner drum, and onto the outer drum, if you're lucky. If you're not, in that case, what we'll do, like I haven't been, is open this with the lights out, and I will, and notice it doesn't let me want to take it off unless the cassette is closed. And once it's closed, I can take it off, and the film is partially on. And then we'll load it in the dark, so as you'd expect. I guess I put too much film in here. Not enough. Anyway, the film should be in there, and if it doesn't go on there, because although a lot of engineering went into this, films have different surface characteristics and curl characteristics, and I've noticed that sometimes when you use amateur films, they tend to be more slippery than maybe, I shouldn't say it that way, than government films. Government films should be more slippery than amateur films, right? So anyway, there are ways to get around that. And this isn't the case where the film is going to fly off the drum, because it's on the inside. So once the camera's loaded, then we can use it to photograph things. Heiser used it to photograph a shutter working. Our project is going to be essentially to take another look at the speed of a .22 caliber rifle bullet. So you'll have at least 2 data points, the one from last week and the one from this week, and you'll be able to make a comparison. What we're going to set up is a self-luminous event. That means we're going to provide the light. We're not going to rely on the shutter. And the self-luminous event will be provided by a schlieren. It's called a schlieren system. What's a schlieren system? This is not about schlieren. Okay, we're about high-speed photography. But schlieren is a technique which is a transillumination technique for lighting subjects. So light is going directly into the camera lens, and the subject is in between. So for that, we use a concave mirror. Some distance away, we put a small light source. Put this so that it's 2 focal lengths away from the mirror. And if we put it 2 focal lengths away, the mirror is going to form an image of that. How far away? Yeah. Anybody want to refute that?
Yeah. Oh, yeah, sorry.
2 focal lengths away, right? So over there will be an image of the light source, upside down, reverse left to right. We don't really care. And over here we're going to put our camera lens and the camera over here, etc. And the picture will be made by the light that comes out of the source, goes to here, comes back to here, and it goes into the camera. The camera is also going to have some light modifier, something called a knife edge. Knife edge could be a number of things. Sometimes it's the diaphragm of the camera lens itself. We're going to use a separate one. It actually just discriminates between light rays that are bent in the schlieren system. And up front here, we'll have our gun. The gun is going to fire around, which will travel across there, and you'll have a shock wave on it if everything goes right. And to make quantification more easier, okay, we're going to know something about this mirror. The mirror has a diameter of 12 inches. And that'll be the scale included in the photograph. So since we know this is 12 inches, then we can make measurements related to that particular known distance. And we'll try to fire the bullet so it's very close to the surface of that mirror, and that way there'll be the scale will be the same in the bullet plane as for the mirror. That's how you minimize scale enhancements. eventually, what we should end up with is a series of images of this field. Okay, with the bullet someplace here, then over here, then over here, then over here, etc. They're not going to be there for too long. Well, it's not going to take it too long to travel across that, because if the bullet travels at 1,000 feet a second, you know, let's assume that that's what it is. It would have to be faster in order for there to be a shock wave, but let's just assume 1,000 feet a second. It'll take it 1,000th of a second to move from there to there, right? So if you were photographing at 2,000 frames per second, it means that in one frame it might be here, the other one will be here, and then the other one is gone. But we're going to run the camera at 20,000 pictures a second. So every 20th, okay, there will be an interruption. Well, it'll move a 20th of that from frame to frame. Although we'll run the camera at 20,000 pictures per second. This is the film. We have these images here, and the other images here. Okay, the offset, I didn't mention how far it was. It's not that important, but it's 14 frames. So the way that the camera goes is, if this is the first one, this is the second one, this is the third one, that's the fourth one, that's the fifth one, that's the sixth one, right? So it goes left, right, left, right, left, right. The framing rate for both columns is going to be 20,000 pictures per second. But I'm suggesting, for the sake of simplicity, that you concentrate on only one set. Because then the time between images is a 10,000th of a second. A 10,000th is a lot nicer to work with than a 20,000th, right? Yeah, I like it when it's easy. So then what do you do? Well, you know the time between here and here is a 10,000th of a second. And you say, okay, well, how fast is this bullet traveling? You're going to find out how far it moved. So you can do it by blowing up this whole thing so that this, you know, scan the thing and make it 12 inches. Or you can work with a known amount of reduction. So you can scale this however way you want. But if you were to go life size, then you can put a ruler here and you can measure this. And you say, well, in this mirror it's 8 inches away from the edge, and this one, you know, it's 4 inches away. So between the two mirrors it moved 4 inches. You know, that's the logic behind it. You find out consecutive positions if you want, or you can go to more than one mirror. Either way. If you go to more than one, maybe the precision of making a decision is better. But always you have to remember that you have to, if you use, let's say, 7 of them, 7 mirrors, the time increments are only 6 of them. The first one is time 0. Even here, 2 mirrors of 2 images. Well, what is the time difference? Well, it's 1 10,000th of a second, not 2, right? Because you subtract 1 out of the 2. So you say, okay, in this particular case, it's traveling 4 inches in, what did I say, a 10,000th of a second? So the velocity, change in distance, a change in time. This is moving at 40,000 inches per second. Yeah. Right? And they say, well, 40,000 inches per second. You say, okay, well, how many feet per second is it? Because normally we don't talk about things moving in inches per second. So you bring it down to a standard feet per second. And so I think you divide that by some number. 12? You figure it out. Mm-hmm. So that's the concept. Now for lighting. Lighting is provided by this lamp over here. And this will be an electronic flash lamp. The duration of the lamp is something in the order of, I think it's maybe a 200th of a second, maybe less than that. So the other thing about the lamp is that it's a non-linear output. Right? It has a very good rise time, but then it decays like that. We will be making pictures by all of this. So in some cases, the first picture may be kind of dark, and then it'll lighten up with time because we're going further and further down this curve. It would be nice if we had a light source like that, but we don't have that. So because the duration is in the order of a 200th of a second or so, we don't have to worry about a capping shutter. So we can just keep the camera running and then fire the gun, get the picture in the camera. Now, what else is going to happen? Or what else do we need to know? Exposure time is going to be, the shutter that we use is a factor 20 shutter. And that means at 20,000 pictures per second, our exposure time will be a 40,000th of a second. And someplace in this thing that there are shutter factors mentioned, and I forget where it is. Okay, one of them is a shutter factor of 1, the other was 2, the other one was 4. So at 4, and I think what we have is a 2. At 4, you'd be getting very close to a millionth of a second per frame. Okay, with 2, we're at 400,000, and at 1, we would be at 200,000. Right? So, oh, remember this drawing, and you look back to this. The light comes in, it forms an image, and then it's re-imaged by a relay system, and then that image is again imaged by a relay system. This tends to be a very light inefficient system. You're losing light left and right. What's the consequence of that? The consequence is that the camera like this demands an awful lot of it. Now, if it's a nuclear blast, you don't really worry about it. But the interesting thing is that as you change the shutter factor, you're also changing the effective F number. The lens is always set to the same F number, but it's the diamond stops that are going to limit the amount of light that goes through. And again, if you look at the specs, I think with the diamond stop that we're using, it where does it say aperture? Shuttering, exposure control. Okay, the level of exposure with each diamond set, it's over here, is F23, F16, or F11. That means F23 with the smallest diamond stop. So you're exposing in a millionth of a second with an aperture of F23, or 22 if you want, even though the prime lens is set to F28. Well, we're running it with a factor 2, so our aperture is going to be F16, effective aperture, at an exposure time of a 400,000th of a second. Now that's what causes you to need a lot of light. You could run through that sunny 16 equation, you can plug in these numbers, and you'll find out that you probably need like 100 times the amount of light that the sun would provide on a nice, bright, sunny day. Light guzzlers. But that's not unusual with high-speed equipment, whether digital or film. You go faster, you need more light. In our case, because we're not or metering this kind of a system, a schlieren system, is not as easy as just sticking a light meter in there. We're going to operate based on experience. And the experience says, well, this has been done before. And we will do it essentially the same way, which is really operating F16, looking at a light source, a bright light source. Just remember this time. I think I remember not too long ago we talked about the exposure time that this camera will deliver at 20,000 pictures per second, right? And that was something like a 400,000th of a second. 400,000th of a second. this happens every time the drum makes one turn. So suppose we keep the camera shutter open, the capping shutter open. Okay. Every time the drum makes one turn, it exposes for this amount of time. It would have to turn 400,000 times before at f16 we would start to make pictures by room line, right? So what do you think a proper aperture shutter speed combination would be here if you were photographing at f16, digital or? Any guess? Suppose you were at, like at f4, what would it be? You get a sense? How much?
30 per second.
A 30th ISO 400. Okay. I don't think we'll need the ISO at this point, whatever it would be. It would be f4 at what do you say? At a 60th, at a 30th. Okay. So f4. Okay. Let's run this camera. Now this one is running at f16. Remember? Let's say we set up the experiment, we get the camera running, it's going, right? Every time, a 400,000th of a second. Now what we'll do is we'll get the camera, or open the shutter, or just move the mirror out of the way. And the minute that you do that, light is starting to go in. So every time now, it's a 400,000. So let's say that we can do the whole experiment. How long? From the time that somebody tells me, fire the gun until I fire it. 2 seconds? 4 seconds. Let's say I'm really slow today, tomorrow. Let's say it takes me 4 seconds. So the exposure time will be 4, am I doing this right? 400,000th of a second? Which is equal to what? 100,000th of a second?
Isn't it one? Isn't it one or four? Yeah, it's 4 turns. So that's 4 turns.
So we're talking about the number of turns in 4 seconds, right? And
so
in 4 seconds, it'll make 400 turns.
No, 4 seconds it'll make 16. Yeah, 16.
It turns 100 times a second.
I thought these oh, how many turns? Right, turns.
It'll be 400.
400 times per second. Okay.
So the exposure time now is, get rid of that. Oops, get rid of 2, right?
Yeah.
Get rid of 2. Now it's 4,000th or 1,000th, right? Did I do that right?
Yes.
So our exposure time is 1/1000th. Even if we keep the shutter open for 4 seconds, our exposure time is 1,000th of a second at f16, right? Hey, that's way away from this. Because we could go, okay, this would be, what should be, let's go to f16 to begin with, and that tells us this. So 5, 6, 8, 11. Okay, so now that we're at 16, so it'll be 15th, an eighth, and 15, a quarter, and a half, right? f16 at a half a second versus f16 at 1,000th of a second. Now with
It's like 9 stops under.
yeah, so I was going to go to figuring, running all that out. But 9 stops difference. We could keep the shutter open for an hour. I'm just exaggerating. It turns out that keeping the shutter open in this lab light is not a big problem. Even if you keep it open for 10 seconds, you won't build up enough density to match this. In the film realm, maybe you want to worry about some other effects. What's an effect? The intermittency effect, right? So intermittent exposures to the film. We're not going to go that way. But the interesting part about this is keeping the aperture or the shutter open doesn't seem to matter. Not in this lab. Now, if you did it in daylight, maybe, but this is the kind of comparison or ratio that you're talking about. So your objective is going to be, from the photographs, to determine the rate at which a .22 caliber bullet flies. And it'll be, last week there was a slight variation, not only between the short and the long, but you all got different longs. Not all different, but some of you got different long bullets than others. Your measurements are not going to match from group to group. But in this case, I haven't made up my mind yet. The same thing might happen, but so you may not be able to compare directly to what you got last week, but yeah, because I don't know who got what. So you'll work with whatever you end up with. What I can tell you, warn you about, is that the bullets should be traveling faster than the speed of sound. And the speed of sound, while I have kind of made light of it by saying it travels at 1,000 feet a second, it's actually faster than that, isn't it? So it's about 11 something. So the bullet speed that you determine should be bigger than that. Otherwise, you wouldn't get a shock wave. I can't think of anything else. That's the end of the afternoon. I'll see you tomorrow. Any questions?